Okay, so let me talk to you guys a little bit more about Jordan form. Again, a matrix is in Jordan form if it has the structure of a block diagonal matrix where each of the block diagonals is itself a Jordan block, as we described last time. I have some more examples a little bit later in this lecture, but anyway, so the theoretical backdrop, for one thing, is if we have a linear transformation on an n-dimensional vector space, and that linear transformation has n eigenvalues possibly repeated, then the good news is that there exists a basis which will put the matrix of T into Jordan form. So that's a very nice result. Such a basis is called the Jordan basis for T. It's not unique, but it is in some sense unique because, like, the order of the blocks could be switched around, which would mean that the basis was, you know, sort of like you could have different reorderings of the basis, but that's kind of about it. So we can easily read lots of data off a given Jordan form. I'll show you more about that today. The algebraic and geometric multiplicities, these are manifest. That means you could just read them straight off the Jordan form if you understand what you're doing. And finally, I would tell you that there is, in fact, a general technique to calculate the Jordan basis for a given transformation or matrix, but I actually don't cover that in your course. Instead, I show you a dangerous path that works almost always for applications. And here's I'll show you a couple examples of this today, actually, but basically the algorithm is simply, first of all, find all the eigenvectors that you can, and then second, you just extend the eigenvectors that you got to chains of generalized eigenvectors as needed. That'll get you into trouble in general, but for us it'll work. Okay, so first of all, let me just talk a little bit about interpretation. So here's a couple of examples, just to expand on the ones I already gave you last class. Example 1. We have this matrix, 4x4 matrix, 1, 2, 1, 0, 2, and 3 like that. So the Jordan blocks here, there's a 1x1 block right here, there's a 2x2 Jordan block right there, and there's a 1x1 Jordan block right there. So this is a block diagonal matrix, and it's the direct sum of the 1x1 Jordan block for eigenvalue 1, the 2 Jordan 2 block for eigenvalue 2, and another 1x1 block for eigenvalue 3. Each block gives you an eigenvector. So eigenvectors here, in fact, are E1, E2, and E3. If the matrix is in Jordan form, the standard basis will be, in fact, a Jordan basis. But generally speaking, finding the Jordan basis requires some work. Anyway, so here, just to collect my thoughts, the eigenspace for eigenvalue 1 is just the span of E1. The eigenspace for eigenvalue 3 is, in fact, just the span of E4. The eigenspace for eigenvalue 2 is just E2. So in the case of eigenvalue 2, eigenvectors are not enough. We need a generalized eigenvector of order 2 to complete the basis, and the generalized eigenvector of order 2, in fact, is just E3. So I didn't talk about this in class, I don't think, but the generalized eigenspace you could define as the null space of A minus lambda I to the m, where m is the algebraic multiplicity of m. Now sometimes this is just 0. For my example, I think many of my examples here, well anyway, this could be 0. Well anyway, more. Alright, so example 2. This is a complex 2x2 matrix. 3 plus 2i, 3 plus 2i. So this is in fact already a Jordan block. It's just a Jordan 2 block for eigenvalue 3 plus 2i. The eigenspace here is 1 complex dimensional. It's just the null space of that matrix, the span of E1. And the generalized eigenspace is the null space of A minus 3 plus 2i squared. In fact, this is the 0 matrix. What I'm trying to tell you is that K1 in this context is nothing more than in fact, K1 in this context would be complex 2 space. Okay? So this example is over the complex numbers, and so is this one. So if I have a, excuse me, looks like this. If you look at that, you can see that there are two, it's block diagonal. This is my example 3. We have two blocks, right? Each block is a Jordan block. That means it's in Jordan form. And what are those Jordan blocks? Well, we have the Jordan block for eigenvalue I, and then Jordan block for eigenvalue minus I. All right. So again, each block gives you one eigenvector. So there's E1 is an eigenvector with eigenvalue I. E3 is an eigenvector with eigenvalue minus I. I mean, you can, if you don't believe me, just try it out. If you multiply A times E1, you'll get I 0, 0, 0, which is IE1. So it's an eigenvector with eigenvalue I. All right. And likewise, AE3 gives you minus E3, minus IE3, so that's an eigenvector with eigenvalue minus I. So the eigenspace for eigenvalue I is span of E1. The eigenspace for eigenvalue minus I is the span of E3. And the generalized eigenspace for eigenvalue I is the null space of A minus II squared. This is actually not 0, but it's got 0 in the upper. When you calculate this, it'll make this block 0, and it'll make that block, I don't even care what it is, it's something non-zero. So this is like 2 complex dimensional, as is K2. K2 is 2 complex dimensional, and it's E3 and E4 span the generalized eigenspace for eigenvalue minus I, because this is the minus I block. All right, then finally, example 4 here. Let's see here. So we've got this 5 by 5 matrix. I have already illustrated the blocks by drawing these little squares for you. We got a 1 by 1 J13. Then there's 2 by 2 Jordan blocks like this. All right. And let's see here. So each block gives me an eigenvector. E1's an eigenvector. E2 is an eigenvector. E4 is an eigenvector, all with eigenvalue 3. So the eigenspace for eigenvalue 3 is the span of E1, E2, and E4. That's all my eigenvectors, up to linear independence, of course. That is also the null space of A minus 3i. If we look at A minus 3i to the 5th, that gives me the generalized eigenspace, because this is the algebraic multiplicity of 3 here is actually 5, right? The characteristic polynomial for this, by the way, the characteristic polynomial for this, PA, I'll use x for a second here, would be 3 minus x to the 5th power. So lambda equals to 3 with multiplicity 5. That's the algebraic multiplicity. So my generalized eigenspace, null space of A minus 3i to the 5th. But of course, this is kind of silly because that's the 0 matrix. What's the null space of the 0 matrix? Well, it's all of R5. All right, or F5 if you want to be, oh look, I'm working over a field that contains 3, whatever. You could make this R or Q or C, I don't know, whatever. 3's in all those. Anyway, the null space, actually A minus 3i cubed is 0 if you work it out. And the highest non-zero power is A minus 3i squared. So that actually is, so again, I'm not going to describe the general calculational method, but in a nutshell, the larger way of, the more general way of doing it is for each eigenvalue, you have to find the largest power of A minus lambda I, which is non-zero, and then followed by the 0, 1. So the fact that this is cubed to 0 and that's not 0, that means at most you have 2 chains with eigenvalue 3. And you can pick any non-zero vector in the any non-zero vector here, and then you can use it to generate the 2 chains. There are two chains here. Anyway, again, I'm not going to get into the details of that. So here's my example 1, and this one, it's got a little bit to it. So it'll take me a minute or 2 here to describe this. So here we go. So first of all, I describe an endomorphism on P2. Let me write that down. So here, T is an element of the endomorphisms of P2R. In other words, that's just a fancy way of me saying that this is a linear transformation from second-order polynomials to second-order polynomials. This right here, folks, is the definition of T. All right. So T of A plus Bx plus Cx squared is given to us to be 3A plus A plus 3B plus 3C times x squared. All right. So given this formula, I can read that the matrix of T, because it's what I need to take ABC and get back to this. So that's going to give me 3, 0, 0, 0, 0, 0, and 1, 3, 3. Because there's no x in the formula, so like the output doesn't have anything in the second component. It's got 3 times the... Anyway, so this is the matrix of t with respect to beta beta. So once I have that matrix, I can calculate the characteristic polynomial of t, all right? Determinant of a minus lambda I. I'm using a instead of t beta beta because I'm going to get tired of saying t beta beta a bunch of times. Anyway, so you calculate the determinant of a minus lambda I, and since it's upper triangular, it's just the product of the diagonals. Woohoo! There it is. So we get lambda 1 equal to 0 one time, and lambda 2 equal to 3. Actually, that's repeated eigenvalue. The algebraic multiplicity of lambda 2 is 2. So I'll start then in the red with calculating the null space of A, which is the eigenspace of 0. So that's this, and then we, what I do? I do a row operation, I can get rid of the 1, I do another row operation, rescale these and put them in the right place. There you go, that's the reduced echelon form. And once I have that, that suggests that if I have u, v, w in the null space, then it's got u equal to 0, and it's got v plus w equal to 0, which means that I might as well just use 0, 1, minus 1 for it, all right? So there's an eigenvector with eigenvalue 0. Oh, incidentally, this proves the fact that 0 is an eigenvalue. It proves that A is not invertible. Fun fact. All right. Anyway, that was one of your suggested after mission 7 problems, which I'll try to talk about from time to time. Okay, moving on. Lambda equal to 3. Well, then I calculate the null space of A minus 3i to find eigenvectors with eigenvalue 3. And so that is that, which is row equivalent to this. And so if I have UVW in the null space of that, so by the way, guys, I use UVW as my like throwaway characteristic, throwaway description of the eigenvector I'm trying to calculate. So this UVW and that UVW are no way related, okay? It's like a disposable notation I use. So anyway, so if UVW is in the null space of A minus 3i, then looking at this, that tells me U is 0, tells me V equal to 0, and it tells me nothing about W. W is free. So I might as well make it equal to 1. The one thing I cannot do is make it equal to 0, by the way, guys. Remember, eigenvectors are non-zero by construction. If you tell me that 0 is one of your eigenvectors, you are telling me, I don't care about your course. I would like to fail. Well, maybe you're not telling me that. But don't tell me 0 is an eigenvector. It's offensive and wrong. Instead, go back and figure out what you did wrong. Because if you're actually deriving through legitimate algebra that 0 is your eigenvector, what that means is that your alleged eigenvalue isn't really an eigenvalue. Right? So, what does it mean if you, let me just, side note here, guys. What does it mean if you're trying to solve, A minus lambda I, you're working on A minus lambda I, V, V vector equal to 0, and you do legitimate algebra and it tells you V is equal to 0. What's that mean? And that's the only solution. That means that this matrix right here is actually invertible, which means that the determinant of A minus lambda I is in fact non-zero, which means that your alleged eigenvalue lambda is in fact not an eigenvalue. So when you find that 0 is an eigenvector through legitimate algebra, you must go search your heart and find the error of your ways. The error of your ways are almost always going to be found back in your calculation of ye olde characteristic polynomial, characteristic equation, because this is tricky and easy to mess up. All right, anyway. All right, enough stories. So let's summarize what we got. We have lambda equal to 3 with algebraic multiplicity 2, and the dimension of the eigenspace with eigenvalue 3 is just 1. So the algebraic multiplicity is larger than the geometric multiplicity, namely 1. So this is where we're going to need a generalized eigenvector. We solve the chain condition. And so I'm going to put V2 is my eigenvector with eigenvalue 3, all right? And then try to solve this chain condition, namely A minus 3i times V3, which we don't know yet, equal to V2. So I use UVW for my throwaway notation. This matrix times that gives me that. So yes, you can make an augmented coefficient matrix and go through the row reductions, but honestly, folks, this is such a simple problem that you're just wasting your time if you do that, because you can just sort through these equations by, hand-to-hand combat. So this first row, nothing. Second row, minus 3v equal to 0. Oh, v is 0. Okay, good. And the third row gives me u plus 3v equals to 1. V is 0, so this tells me u is 1. Again, no condition on w, which we could have foreseen by this column of zeros right here. So w is free, and in this case I can set w equal to 0 because I've got something else non-zero. And this gives me v3 is 1, 0, 0. In summary, my gamma bar, 0, 1, minus 1, 0, 0, 1, 1, 0, 0, is a Jordan basis for A. And in particular, we could prove, if you do the calculation, that if we calculate the inverse of the basis matrix times A times the basis matrix again, it will work out to this. It will work out to the 1 by 1 0 block, a Jordan eigenvalue 0 block, and then a Jordan 2 block for eigenvalue 3. In other words, this will similarity transform A to a Jordan form, which means that this gamma bar is a Jordan basis for A. All right, and I'm actually interested in the original endomorphism of the quadratic polynomials, the t. So I can actually go backwards. I can take this basis and I can translate what that means back to the t. So translating back, if I have that coordinate vector for a polynomial, the way I ordered the polynomials back in the statement of t, right? Let me get back to it. My beta basis had 1x squared. So when I look at this, I go x minus x squared. I look at this, that translates to an x squared. I look at 1, 0, 0, well that's a 1. So this suggests to me that x minus x squared 1 is in fact a Jordan basis for the transformation. And I claim that if we calculate t gamma gamma, we're going to get this block decomposition in terms of Jordan blocks. Now, don't take my word for it. Let's just calculate it and make sure I'm on the straight and narrow here. All right. So continuing, let's take gamma to be the alleged Jordan basis and see for t. So there's my basis. I need to take a linear combination of these, like this: a times the first thing, b times the second thing, c times the third thing. So reformulating that, that's t of, and I've got an extra, I'm sorry, I meant to wipe that out. Stink. Oh, I need scratchy. All right. Sip some coffee here. Okay, so multiplying this out, collecting the constant term, you know, the linear term, the squared term. Remember how we defined t to start with? So here's the definition of t. It takes the constant thing. So in other words, the c doing, you know, c is like the a. When you look at this, the b is playing the role a does here. You know, b and a are, and the c is getting taken over by b minus a. Oh, be quiet, you beto. Stupid phone. Sorry about that. So anyway, going back to the definition of t, I multiply the constant term by 3, and I take the sum of the constant term and then 3 times the middle term plus 3 times the coefficient of x squared. So that's what I did here. And then I reorganize it. I just simplify things. And then I'm like, okay, well, in order to see what the matrix of t is with respect to the gamma basis, I need to express the output as a linear combination of these guys, right? So if you look at it, you have to put 0 times x minus x squared, because there's no x up here. So I wrote that. And once I wrote that, it became clear that I had c plus 3b times x squared, and then plus 3c. Okay, so what's the matrix with respect to gamma? Well, I have this with coordinate vector ABC, maps to this image with coordinate vector 0, c plus 3b, 3c. And so, lo and behold, we have this matrix with respect to the gamma basis, namely 0, 0, 0, 0, 3, 1, 0, 0, 3. In other words, it is in fact in Jordan form. Woohoo! Alright, so this is a roadmap for how to calculate the Jordan basis for a linear transformation. What you do, or at least one way to do it, unless there's something else you know, freely available to work with, is pick any old basis for your vector space. You find the matrix for the transformation. Then, for that matrix, you find the characteristic polynomial. You calculate the eigenvectors and then generalized eigenvectors as needed for the matrix. And then you can take that and translate back to get the corresponding generalized eigenbasis on the vector space like I just did here. In my current notation, you find the gamma bar for the coordinate vectors, and then you translate back to gamma, the Jordan basis for t itself. Anyway, I have another example, so that should help if you didn't understand that just yet. Let's see here. And I think I have easier examples in the notes, which I'll get to after I'm done with this stuff. All right, so example 2, suppose we have the span of e to the t, te to the t, t squared e to the t. And I'm going to look at the transformation that's defined by differentiating this. All right, and by the way, this is well defined because if you take the derivative of these functions, you get a linear combination of these functions again. All right. Okay, so what I do, I pick a basis, and I just use the one that's kind of given here in some sense, this one, and I write down what does this transformation do. It takes this and maps to that, right? Product rule, right guys? Then I collect things. So I've got a copies of e to the t here, I've got b copies here, so I got a plus b e to the t. Where do I got bt, and I got 2ct over here, so I got b plus 2ct e to the t. And where's my t squared? So I got c t squared e to the t, so I got that. All right. So if this goes to that, you can see that in the beta basis, we've got matrix 1, 1, 0, 0, 1, 2, 0, 0, 1. Now that is almost already in Jordan form, so this calculation is a little bit easier than the last one we did. I can look at this, and because it's upper triangular this time, and so the eigenvalues are on the diagonal, 1, 1, 1. Because it's obvious if you calculate this that the characteristic polynomial would be, p of lambda would be 1 minus lambda cubed. So we get lambda equals to 1 with an algebraic multiplicity of 3. All right, so then I go looking for my eigenvector for the matrix. All right, call A the matrix. So A minus I is this, which is rho equivalent to that. So this tells me that my UVW eigenvector has v equal to 0, has w equal to 0, so u is free, as we could have anticipated from this lovely column of zeros corresponding to the u. And so that gives me eigenvector 1, 0, 0. In other words, the dimension of the eigenspace here is 1. So we have a geometric multiplicity of eigenvalue 1 of 1. Now, since that's the only eigenvalue for A, we must have a 3-chain. For lambda equal to 1. And in this case, we can anticipate that, in fact, the Jordan form here is going to be 1, 1, 0, 0, 1, 1, 0, 0, 1. Now, that's nice to anticipate it, but let's see what it actually is. Let's work it out. So continuing, I work my way up the chain. Let's make sure I got my thing in. Nothing makes me sadder than to find out I've been working outside the view. So I work my way up the chain. I take my eigenvector 1, and I find my generalized eigenvector v2 of order 2 by solving this chain condition. That's the same matrix we already looked at for the eigenvector calculation, right? It's kind of the cute thing is, yeah, I'm finding an eigenvector with generalized eigenvector eigenvalue 2, but I never actually have to square this matrix even. It's funny how that works out. So this gives me that this gives me v equals to 1, this gives me 2w equal to 0, and this gives me nothing. So in short, I got v equal to 1, w is 0, u is free, so I might as well just put u equal to 0 as well. I get v2 is 0, 1, 0. I make things 0 whenever I can as a rule of thumb, guys. Okay, then I'm going to keep working my way up the chain. I look for a minus I v3 equal to v2. If I can solve this, this will make v3 a generalized eigenvector with eigenvalue 3. Generalized eigenvector with eigenvalue 1 and order 3. Okay. So again, same matrix, but now equal to the v2, which is 0, 1, 0. And so that tells me v is 0, that tells me 2w is 1, no condition from the third. So I'm forced to put 0, 0, 1 half. All right. Now that gives me gamma bar, E1, E2, and then 1 half E3 is a Jordan basis for A. Now let's just check our work since it's pretty easy to do here. AE1 is E1, that means E1's an eigenvector with eigenvalue 1. All right. And it'd probably be helpful for me to actually write A on this page. What was A? A was 1, 1, 0, 0, 1, 2, 0, 0, 1. So that's the A, right? All right. And so you can see that AE1 is E1. You can see that AE2 is 1, 1, 0, because that's the second column. So that's E1 plus E2. You can see that if we multiply 1/2 E3, we get 1/2 of the third column, which is 0, 1, 1/2, which is, by the way, also E2 plus 1/2 E3. So rewriting it, we've got A minus I E1 equals 0, A minus I times E2 is equal to E1, and finally A minus I times 1/2 E3 is equal to E2. So these are the chain conditions. All right. And anyway, so if we similarity transform our A back to where we started, we will get 1, 1, 0, 0, 1, 1, 0, 0, 1, which is a 3 by 3 Jordan block for eigenvalue 1, just as we had hoped. But now I actually explicitly give you the basis which makes that happen. Now I can translate back to the original polynomials, function space, and I can tell that gamma being e to the t, t e to the t, and 1/2 t squared e to the t will serve as a Jordan basis for t itself. Indeed, e to the t is an eigenfunction for the differentiation operator. T e to the t is also an eigenfunction for the differentiation operator, because when you differentiate t e to the t, you get back, this is not an eigenfunction, right? You get back t e to the t plus e to the t. That's actually a generalized eigenfunction with eigenvalue 1 and order 2. See, because this right here is the same, right? That's the same as t minus the identity map on V2 equal to V1, right? And this over here gives us t minus the identity map acting on V3 equals to V2. So yeah, this 1/2 t squared e to the t is a generalized eigenvector with eigenvalue 1 of order 2, and when you differentiate that, when you multiply this by t minus the identity, you get to V2. When you multiply t minus the identity on V2, operate on it rather, you get V1. So in short, that's the top of the chain, and differentiating it, operating by t minus I on this, t minus the identity on this gives me that. That gets me to that. So anyway, long story short, it's a Jordan basis. All right. Finally, I have an example of a complex eigenvector for a real matrix. This is where we're going to next, is talking about how do we deal with complex numbers and their relation to real numbers as it relates to matrix problems. Okay. So I think this is a good starting example because it just shows you a lot of the things we're going to try to understand in the next about hour and 20 minutes of lecture or so. So let's just start here. So suppose you got this 2 by 2 matrix. What we've already talked about for the last hour and a half or so in lecture, there's nothing that stopped us from finding complex eigenvectors for complex or real matrices, right? Well, in the sense that any real matrix could also be viewed as a complex matrix, right? So, so this one here, suppose we have the 16, 6, minus 15, minus 2. Find the complex eigenvectors for A. All right, so I look at the characteristic equation, I get this times that plus 90, I rearrange it, I get lambda squared minus 14 lambda plus 58. Completing the square is huge here, guys. So lambda minus 7 squared plus 9 completes the square. And once I see this, I can read directly from this that the eigenvalues are 7 plus or minus 3i. So the complex eigenvalues, right? So if we regard this as a real matrix, we'd say, well, there are no real eigenvalues, all right? If we regard this as a complex 2 by 2 matrix that just happens to have real entries, well, then it has eigenvalues, and here they are, 7 plus or minus 3i. So context matters. Whether or not a matrix has eigenvalues depends on where you say it lives. Okay, anyway, so let's study this then. We have 7 plus 3i as our complex eigenvalue. So I need to find the null space of A minus 7 plus 3i times I. That's this 2 by 2 matrix. which by the way, if we rescale by dividing by minus 15 is that. And then if we simply multiply the lower row by 9 minus 3i, it turns out that this simplifies to 6 because 9 minus 3i times 9 plus 3i is 81 plus 9, which by the way is 90. 90 over 15 is 6. So rescaling the bottom row by 9 minus 3i gets us to that. As you can see, and as we should expect, both rows are actually linearly dependent. It has to be the case. If these were actually distinct rows, that would mean that this is an invertible matrix and only the zero solution would exist. So you know, if you haven't made a mistake calculating your eigenvalue, the 2 by 2 matrix problem must have only one independent row at most. Okay? So in some sense, I'm telling you that this calculation actually is not needed. If you're confident about your selection of lambda, you can just pick either equation and go with it, and you won't be wrong. I was just checking our work again here to show you, that it is in fact legitimate. So anyway, I will work with this equation, 9 minus 3iu plus 6v. Solve for v, 3i minus 9 over u over 6 times u. So I make u equal to 6 because I don't like fractions. U equals 6 gives me v is equal to 3i minus 9. Consequently, my eigenspace with eigenvalue 7 plus 3i is the span of 6, 3i minus 9. Now, beautiful thing here, to find the eigenvector for the other eigenvalue, we can get it from simple complex conjugation. If our matrix is real, then when we take the complex conjugate of the eigenvector equation here, right, what happens is A conjugate's equal to A, and when I take the complex conjugate of this, I get 7 minus 3i. Complex conjugate of I is just I again. The complex conjugate of V is, well, V star. And V star specifically is, we just put I to minus I, so we get 6 minus 3i minus 9. So without any additional work, I can already tell you the eigenspace of the other eigenvalue, the 7 minus 3i, is the span of the conjugate eigenvector. Very cool. And so what's this all mean? Well, this means that the 2 by 2 matrix, 2 by 2 real matrix, 16, 6, minus 15, minus 2, has eigenvalues, and I'm going to call them lambda plus minus, or 7 plus or minus 3i. In particular, we have AV plus is lambda plus V plus, where V plus is this complex vector. We have A times V minus is lambda minus V minus, where V minus is this complex vector. The V plus and V minus are related by complex conjugation. All right. And so in short, if we were to make the basis V plus V minus like that, we would find that A is similar to a diagonal matrix by this calculation beta inverse A beta, and that diagonal matrix would be 7 plus 3i, 0, 0, 7 minus 3i. Again, this falls back on that calculation that the theorem we proved in general, that A is diagonalizable, if and only if there's an eigenbasis. So this matrix A, this real matrix viewed as a complex 2 by 2 matrix, is in fact complex diagonalizable. Here it is. This is its diagonalizable form, diagonalized form. However, A is not real diagonalizable because A has no real eigenvalues. So no, A is not real diagonalizable, yet A is complex diagonalizable. However, we can say something real about this. It is what's called the real Jordan form. What you can do is you can take the real part of the complex eigenvector, the imaginary part of the complex eigenvector, which here are 6 minus 9 for the real part, 0, 3 for the imaginary part. Those are two-dimensional real vectors, all right? And this particular basis will form, I call it the real Jordan basis in the notes. This particular basis will form, by similarity transformation, it will take A and it will convert it into this, 7 minus 3, 3, 7. This right here is one of the fundamental building blocks for the real Jordan form. So real Jordan form of A. So again, strictly speaking, this is not a Jordan form since A has no real eigenvalues, but this is what I call, quote unquote, the real Jordan form. So just to give you the, sort of quick explanation for what's going to happen, we're going to be able to show that if we look at a real matrix, its eigenvalues are either real, right, or they're complex. But if it's complex, they come in conjugate pairs. And so the complex eigenvalues, each one of them will give us complex eigenvectors for the corresponding complex matrix. Well, viewing the given real matrix as a complex matrix, rather. And each complex eigenvector will give us a pair of real vectors, which we can then use to construct a basis, which puts the matrix in a special form, which we call the real Jordan form. All right, so it's hard for me to say much more about that without showing you some further examples here. So yeah, I'm going to stop and start again. I gotta get a drink right quick.